Okay, finally example 3, 2 plus the square root of 15 over the square root of 5. Basically the same structure the last problem was. Once again, the problem is the denominator being a radical. We don't want that. So the fix is multiplication by the square root of 5. If I multiply the bottom by the square root of 5, I'm required to multiply the top by the square root of 5. And once again, the top is a binomial structure, so I do have to distribute the square root of 5 through the binomial to multiply. If I multiply square root of 5 times 2, not a radical times a radical, just makes those two pieces put together. Right here I have a radical times a radical, so I'm going to get the square root of 75. 15 times 5 being 75. Both underneath the radical, so I'm allowed to multiply underneath the radical to get that product. And on the bottom I got the square root of 5 times itself, which just makes 5. So right now I've simplified it to that extent. One extra added feature to this one though, and I forgot to mention the last two problems because it didn't really happen in those two problems. I think we're getting used to these numbers that can be broken down. But do look for a possibility that we can reduce these radicals. This is the way we've been reducing them. If I did a factor tree for 75, it's 3 times 25. 3 is prime, 25 is 5 times 5. So I'm doing the square root of 75, it's this. There's a pair of 5s, I can pull a 5 out. You should, I'm expecting you to do that every single time you look at radicals. Notice that it's a reducible radical, you should reduce. So I can't make 2 times the square root of 5 any prettier because 5 is prime and has no perfect square factors. Square root of 75 we broke down to 5 times the square root of 3. And all that's over 5. And again, if I'm looking to possibly reduce, what I'm focusing on is the lead numbers. So 2, 5, and 5. Any number to evenly divide 2, 5, and 5? No. So I can't reduce it. These radicals are different, so I can't add them together. So that's the best I can do for that one. So that's my final answer.